Okay, so at this point in the semester, we have talked about rationalist functions and polynomial functions, which are both very important. But today we're going to start talking about exponential functions, which are just functions with the property that the variable is in the exponent. So that's with the variable is in the exponent. Okay, so that's something like y equals 2 to the x is an example of an exponential function. So rather than having a variable raised to some power, or constant power, we have a constant raised to a variable power. And exponential functions are incredibly important because they show up in all types of real-world applications, in science, and in biology, and in finance, just to name a few. And so we're going to look at these in quite a lot of detail over the next 5 sections. Okay, so first off, let's look at the graph of what an exponential function looks like, and it depends on the base. So all exponential functions either look like this blue curve right here, and that's if b is greater than 1, okay? Or they look like that red curve right here if b is between, if b is between 0 and 1. Okay? So, let's see here. So if b is greater than 1, then we have something like that. If b is less than 1, then it looks like this. Okay? Now, in either case, the domain is going to be all real numbers, so from negative infinity to infinity, and the range is going to be from 0 to positive infinity if you have something of the form y equals bx, b to the x. And also the horizontal asymptote is going to be equal to 0. Okay, so in either situation you get those 3 properties. And so you notice a couple things here. First, if you have y equals b to the x, then the function is definitely going to pass through the point 0, 1. And that's because b to the 0th power is going to be 1, so y will equal 1. Okay, so this is kind of like the one standard point. These things don't have they don't have a vertex per se, like a parabola does, but they do have this point, which is kind of like a base point. Okay, so if you remember that, that'll help you graph these functions and it'll help you shift these functions. So what I'd like to do is start with example number 1, and I'd like to plot g of x equals 1/2 to the x by just picking some points and plotting them. So I'll start with x values over here, and I'll write y equals 1/2 raised to the x over here. So let me do like 0, and like I said, 0, well, you get 1/2 to the 0th power is 1. So again, this goes through the point 0, 1. And if I plug in -1, I'll get 1/2 to the -1, which is 2 to the first power. So that's just 2. So -1, 2. If I plug in -2, I get 1/2 to the -2, which is going to be 2 squared, or 4. If I plug in -3, I get 1/2 to the -3, which is 2 cubed, which is 8. And if I plug in 1, I get 1/2 to the 1, or just 1/2. And if I plug in 2, I get 1/2 squared, which is 1 over 2 squared, which is 1/4. And if you plug in 3, you get 1/8. Okay, so you can see that this graph is growing very quickly to the left of the y-axis, and it's shrinking very quickly towards 0 to the right. So it's moving towards the horizontal asymptote of y equals 0. So maybe I'll write that in red, that this y equals 0 is my horizontal asymptote here. Okay. So now if we want to just change this up a little bit and graph, I don't want to call that g of x. I want to call that, let me do this in purple. I want to call that h of x. So I want to graph h of x equals 1/2 x plus x at 1/2 to the x plus 1 minus 3. Okay, and I'll do that by, again, well, we can either do it by plotting points or we can do it by shifting. So x, and let me say h of x equals 1/2 to the x plus 1 minus 3. Okay, so there's two different ways you can go about this. You can either just plug in some points, like we did before, or you can figure out what the necessary shifts are based on the exponent, which is x plus 1, and then the minus 3. And I'll kind of walk you through both. Okay, I'll walk you through both processes. So let's start by plotting points, and then I'll tell you how you could have done the same thing with less work if you know how shifting the graph works. Okay, so if you plug in 0, then you get 1/2 to the 1 minus 3, because 0 plus 1 is 1. So that's 2.5 or negative 2.5 or negative 5/2. Okay, so 0, negative 5/2 would be right about there. If you plug in negative 1, then you get 1/2 to the 0 minus 3, which would be the same as 1 minus 3, which is negative 2. Okay, so that's negative 1, negative 2. And I'm going to highlight this point as kind of like an important point, and that's because that's where the 1/2 was raised to the 0, and then we subtracted 3 from it. So it's kind of like if 0, 1 is a base point, then negative 1, negative 2 was kind of my base point of this graph. I'll say more about that in a minute. Okay, let's just complete this graph by filling in more points. If I get 1/2 to the negative 2 minus 3, that is the same as saying 2 to the squared minus 3. So that's 4 minus 3. Oops, sorry. If I'm plugging in negative 2, then that's negative 2 plus 1 minus 3. So it'd be negative 1/2 to the negative 1 minus 3, which is 2 minus 3, or negative 1. So long story short, that's negative 2, negative 1. Now I want to plug in negative 3. So it's 1/2 to the negative 3 plus 1 minus 3. So that's 1/2 to the negative 2 minus 3, which would be 2 to the squared minus 3, or 4 minus 3 is 1. So 3, 1 is a point there. And then if I keep plugging in, if I plug in 1, I get 1/2 to the 1 plus 1 is 2 minus 3. So it'd be 3 minus 1/4. So 3 minus, or sorry, 1/4 minus 3 is the same as 1/4 minus 12/4. So that's negative 11/4. So that'd be right about here. And if I plug in 2, I'm going to get 1/2 to the 3rd minus 3, which would be 1/8 minus 3, which would be 1/8 minus 24/8. So that's negative 23/8. So just a little bit bigger than negative 3 there. Okay, you can kind of see that my horizontal asymptote in this case is going to be y equals negative 3, and that the graph is growing something like that. Okay, now let me talk about how you could get this from shifting. So we have h of x is 1/2 to the x plus 1 minus 3. So notice that if x equals -1, then h of -1 is 1/2 to the 0 minus 3. Okay, so the fact that I'm raising 1/2 to the 0, and I'm going to get 1, that's like the 0, 1 points. That's like my base point. And then I'm going to subtract 3 from the y value. So what that's telling me is that this -1, -2 is kind of like my 0, 1 in the blue graph. So to get there, what did I do? I shifted left 1 unit. So this x plus 1 is telling me shift left 1 unit, because x plus 1 will equal 0 when x equals -1. So it's telling me to shift left, and then the -3 is telling me to shift down 3 units. So really it's not that surprising then that the horizontal asymptote of this new shifted graph is y equals -3, because I'm just shifting the old horizontal asymptote, which was y equals 0, down 3 units. Okay, so you can either look at this as taking this graph and shifting down 3 units into the left 1, or and down 1, or sorry, left 1 unit, down 3. Okay, so I could fill out the rest of this blue or the purple graph by looking at all the different points on the blue graph and just saying how do I get, or what happens if I shift left 1 and down 3. So that point corresponds to that point, and if I plot this point here, that's -3, 8. I should go over 1 and then down 3, and that should be a point on my purple curve. Okay, so every point on the purple curve should be to the left 1 and down 3 of every point on the blue curve, of a point on the blue curve, I guess. That's the takeaway there. Okay, now I want to talk about the natural base e. E is an irrational number, which is approximately 2.718281827. And this is an extremely important number in nature. I would argue this is because it's calculus's favorite number, but let's just leave it at that this shows up all the time in nature, and you should know at least the first 4 digits. You should know 2.718. If ever you're asked to approximate e on a calculator or something, just type in 2.718. Maybe you'd want to know the first 5 digits, 6 digits, that'd be good. NASA actually has a database of the first 1,000,000 digits of pi, so they consider this number very important because there's actually just an entire web page dedicated to the first 1,000,000 digits of pi. Okay, so the function f of x equals e to the x is called the natural exponential function. So it's an exponential function whose base number is e, or 2.718281827, and you should continue that on with infinitely many different digits there. Okay, so that's the natural expression. We'll see that in a second. Now for example 3, what I want to do is just walk you through how to evaluate exponential functions in your calculators, because your scientific calculators have a very special way of entering these things in. So the first thing you're going to do if you want to evaluate 3 to the -2.9 is you would hit the 3 key, and then the exponential key is y to the x. So there's a y to the x button, and then you're going to plug in 2.9, and then you're going to hit plus or minus. So what that is doing is it's saying take 3, raise it to some power, and that power is going to be -2.9. So you had to enter in 2.9 and then make it negative by hitting the plus or minus button. And then you hit the equal sign. And what you should get is 0.041. Okay? And you should round to 3 decimal places because that's what I asked for here. Alright, now if you want to do e to some power, then what you do is you type 0.55. Okay, that's the exponent. And then you hit second and the ln button. Well, the ln button is natural log, And if you hit second, you can see that e to the x is like is a light color on that button. So when you hit second, you're saying I want to use the second function, which is e to the x. So this is e to the x to the 0.55, and then you hit equals. And you should get 1.733. Okay? So we'll get some more practice of that in a minute. Hopefully that's clear what the process is to actually evaluate using your calculator. Okay, so now here's an example 4. It's a real-world word problem. It says that the 1982 explosion in a nuclear lab sent about 1,000 kilograms of a radioactive element into the atmosphere. The function f of x equals 1,000 times 0.5 raised to the x over 30 describes the amount f of x in kilograms of the radioactive element remaining in the area x years after 1982. If even 100 kilograms of the radioactive element remain in the atmosphere, the area is considered unsafe for human habitation. So it asks us to find f of 40 and determine if the area will be safe for human habitation by 2022. Okay, so maybe read that again aloud to yourself and try to figure out what the question is asking. Okay, well, it says that f of x is 1,000 times 0.5, or 1/2, x over 30. And what we're asked to do is we're asked to find f of 40. So I'm going to plug in 40 for x. We're looking for how much radioactive material is left 40 years after the accident. And so I'm going to have 40 over 30 as my exponent, or 4/3. So we're really looking for f of 40 is 1,000 times 1/2 to the 4/3, which you could write as 1.333. And what you should get is 396.85 kilograms. And that's much more than the 100 kilograms that was considered safe. Okay, so the takeaway here is that it's not safe to live near that spill site yet. And now to evaluate this, what you could have done is you could type in 0.5, and then you could type in y to the x, and then you could type in 1.333 and put in a whole bunch of 3's, because that's 4/3. This is an approximation of 4/3, and so we're rounding down if you do decimal expansion. And then you hit equals. And then you can take that number and multiply it, so hit x times the 1,000, and then hit equals again. And that should give you the 396.85. Okay. So there's one word problem. Another place where this shows up, or where exponential functions show up, is in compound interest. So in banking or investment functions. That's going to be given to you by a compound interest formula, which is really important to know if you're going to invest or if you're going to go into debt. You should really understand how exponential growth works. So if you have a credit card or a student loan or a car payment or a mortgage payment, you really need to understand how exponential functions work. So hopefully that's enough motivation, because I'm pretty sure most of us in this class have one of those: a credit card, a student loan payment, a mortgage payment, a car payment, any sort of debt. Or hopefully we also have investment funds, like your 401k, your Roth IRA. All of those use exponential growth for the compounding growth. Okay, so it says here that compound interest is interest computed on your original investment as well as on any accumulated interest. After 2 years, the balance A in an account with principal P and annual interest rate R is given by well, it's going to be a equals p times 1 plus r over n to the nt if you're compounding n times per year, or if it's compounded continuously, like every second or every millisecond, it would be a equals pe to the rt. So again, p is the principal. That's how much you have invested at the initial time, or the time 0, let's say. And then t is the time n years down the road, time t years down the road that you want to know how much you're going to have in your account. N is the number of times you compound per year, and r is your interest rate. Okay, so let me just say that some common values for n here are semi-annually. So if you see semi-annually in a word problem, that means n is equal to 2. You're compounding once every 6 months. Okay. If you see quarterly, then that's n equals 4, because you're doing once every quarter or once every 3 months. If it's monthly, then it's n equals 12. And then daily would be n equals 365, because you're doing it 365 times per year. And then continuously means every second or every millisecond or something. As often as possible you're compounding whatever you have in the account. And so n disappears from that formula. You just have pe to the rt. And that's because the 1 plus r over n to the r, that goes, to the n, that goes to e to the r if you take the limit as n goes to infinity. So that's just like a side note. You don't really need to know that, but that's part of the reason why e shows up. Okay, so now it says find the accumulated value of an investment of $5,000 for 10 years at an interest rate of 6.5% if the money is compounded quarterly. So you have $5,000, you invest it in an account that earns 6.5% interest, and you want to know how much money is left in that account 10 years later, or how much money have you made. And the formula says that you should do A equals, because this is compounded quarterly, it's 1 plus r over n to the nt. So in this case, P is $5,000. We want to find A. Our interest rate is 6.5%, which if you write that in decimal form is 0.065, because percent means per 100. So you're taking 6.5 divided by 100 will give you 0.065. And now you're dividing by n, the number of times you're compounding per year. Well, this is compounded quarterly, so this is going to be a 4. You're compounding 4 times per year. And then it's n times t. T is 10 for 10 years. So it's, again, 4 times a year for 10 years. And if you plug that into a calculator, you should get about $9,527.79. Okay. So you've made about $4,527 just by sticking this money in the bank and leaving it there. It'd be nice if banks actually paid 6.5% interest right now, but they don't. But there are other investments that would pay more than that, on average, let's say. Okay, so now if the money is compounded continuously, you get a slightly different formula. It's a little bit cleaner. It's just A equals P e to the RT. And again, this is like it's compounded every second or millisecond. So that would be 5,000 times e to the 0.065 times 10. And if you plug that into your calculator, you should get $9,577.70. Okay, and so this is about $50 more than in the previous model, and that's because we've compounded more. So the thing has had the opportunity to compound more frequently, and so it's just a little bit bigger, about $50 bigger. And so this is one important lesson to note, is that if you can compound more frequently, you'll end up making more money, which is why typically banks or mutual funds will pay out once every quarter, but then banks, when they're charging like interest, will try to compound at least once every month, like credit cards do, or continuously, because it will mean they'll make more money. Okay, so be aware of that. You should look to see how often your debt is compounded, or your interest is compounded, depending on whether you're investing or owing. Okay, that's it. We'll do lots more world problems like this in class because I consider this to be a very important application. See you guys on Thursday.